So hello everybody, this is the third and last video about calculation of phi of n before we go on to other mathematical foundation of RSA. So actually, if you want to compute phi of n without using the full list of elements of z over nz and computing this GCD, actually, there is another method which is based on three statements. The first one is if p is a prime number, and it's a property of a prime number, that its GCD with the values which is strictly less than p is always 1. So actually this is translated as phi of p is equal to p minus 1. So let's remember the example about 7. Actually, as 7 is a prime number, phi of 7 is 7 minus 1 is 6. And this is true for all prime numbers. Second statement. If p is a prime number and k some integer number greater than or equal to 2, then phi of p to the power of k is p minus 1 times p to the power of k minus 1. So we'll have examples of how to use those statements. So next and last steps, actually, how can we handle numbers which are not prime numbers or powers of prime numbers? So if the GCD of two numbers a and b is equal to 1, that is, if a and b are coprime or relatively prime. So I would like to have your attention on the fact that this doesn't mean that a or b is a prime number. So any two numbers might be coprime. Okay. So if a and b are coprime, then phi of a times b is equal to phi of a times phi of b. And actually, those three statements are enough to have an algorithm able to calculate the value of phi for any value of n. So again, examples. So let's use a value previously used. N is equal to 7. 7 is a prime number. So we use the statement number 1, phi of 7 is equal to 7 minus 1 is equal to 6. Second example, n is equal to 15. Actually, 15 is not a prime number because it's 3 times 5. It's not a power of a prime number, so that we can't use statement number 1 or statement number 2. So we will use statement number 3. So as the GCD of 3 and 5 is equal to 1, and please remember that before using statement number 3, you have to make sure that the GCD of two values is equal to 1. So I'll take an example to show you how all this works. So as the GCD of 3 and 5 is equal to 1, what we can write is that phi of 3 times 5 is equal to phi of 3 times phi of 5. Then, from this decomposition, actually statement number 3 helps us decompose number until we get the possibility to use statement number 1 or statement number 2. Now, 3 is a prime number, so phi of 3 is equal to 2. On the other hand, 5 is also a prime number, so we can still use statement number 1 to write phi of 5 is equal to 4. And from those values, actually, sorry, that's just something below on the table, just forget it. So phi of 15 is equal to phi of 3, which is 2, times phi of 5, which is 4, is equal to 8. So that's not a surprise that we find exactly the same value that than with the other method, but this one is, let's say, a little faster because you don't have to have all the lists of elements and try to compute the GCD in Z over NZ. So that's all for that little video, and the next one will be again a set of examples here to use this faster method.